will bring us through machine learning techniques for process monitoring, control, and optimization. The experience of John is interesting because they started as perceptive engineering. They built up a very great portfolio, great success, and then they ended with a very successful acquisition. So congratulations once again.
Thank you.
Thank you very much.
Today, I'm going to give a little bit of a different talk. We're going to go in a slightly different direction to the rest of the conference. I'm going to talk about another industry, the semiconductor industry, and maybe just make some parallels, some connections there between our industry and the pharmaceutical industry and what's happening in the semiconductor industry. I've called the subtitle here a semi-intelligent view. That may be related to the semiconductor industry. It may be related to the cognitive skills of the speaker. I'll let you decide towards the end of the presentation. So let's get started. So I'm going to go through an introduction to applied materials. We're going to go through a little bit about the semiconductor story, some case studies, and then we're going to wrap up with some semi-intelligent conclusions. So first of all, Applied Materials, potentially the biggest company you've never heard of. So we're the world's #1 in terms of the manufacturing ecosphere for semiconductors and display equipment. We have 100% install base in all of the wafer fabs in the world. So probably all of you today will use technology that's been manufactured using Applied Materials process equipment and automation platforms. Very heavily focused on R&D. We have over 15,000 patents. One of the original companies in the Valley in California, and actually up to 32,000 employees now. So we've been growing very successfully over a number of years. And essentially now, over the last 5 years, Applied has been moving into taking this technology into the pharmaceutical industry as well. So let's have a look at the story of a semiconductor. So we now have a supercomputer in our pockets. If we took the technology from the 1980s and tried to build an iPhone, it would cost $110 million. It would consume 200 kilowatts of energy, enough to power 2 Tesla Model X's. If you've ever seen a Tesla Model X, 2.5 tons, going from 0 to 100 in 3 seconds, that's a lot of energy. And how tall would this phone be? Anybody like to hazard a guess? It would be 14 meters tall. If you're familiar with Dom Jolly and Trigger Happy TV, that's a big phone even for him. So yes, it's very interesting to see how we've expanded. So how do we make such a chip? Well, we start off with a crystal ingot of silicon dioxide, and we slice it into thin 300 millimeter wide wafers. We then apply a pure silicon layer, then a layer of photoresist, and then we begin an etching process. So using templates and highly sophisticated etching, we form the patterns required for the circuits. Layering upon layer, we build this up, we build transistors. We can have multiple transistors in the layers, and then we need to connect those transistors together. 12.5 miles of wiring in a CPU in a phone. 12.5 miles. It's pretty incredible. From there, we then cut it into single chips, and we package those chips with the wiring, and we test them, and we release them. I really like this slide because it's completely out of date. It's from 2018. Things move fast in the semiconductor space. So we can see here 12 billion transistors in a chip. That's actually 40 billion now. 40 billion in a GPU. There's a lot of junctions and a lot of complexity. So some numbers. I won't go through all of these. These are some of the numbers in terms of a semiconductor fab. The semiconductor industry is not the pharma industry. I get this. We can't make these are not meaningful comparisons, but take a look at the likes of the OEE and the process capability. Just to put this into context, if a semiconductor fab is down for 1 day, that's $10 million in depreciation alone. These fabs generate $1 million of value per hour. So we're talking big numbers. And if we get it wrong, it goes wrong dramatically well. So we also have, the likes of, look at the data points in terms of the data collection, the throughput. These are all, pretty big numbers in terms of those the statistics. Anyway, enough of the semiconductor industry. Let's go back to what we do here, right? Commercializing a continuous process. Let's have a look at our industry perspective. And what we're trying to do here is really speed up that S-curve, that transition from R&D, pilot plant, ramp up the yields into manufacturing. We want to close that gap in terms of productivity. So we characterize our unit operations. We integrate those unit operations into a process train. Then from there, we apply sensors, monitoring, advanced process control. And we integrate that into the factory. That's a really good workflow for a commercial process for the semiconductor industry. So we're seeing some parallels already. We're using some slightly different words. We have metrology instead of PAT, for example. We're using different terminology, but essentially we've got the same concepts. So we can take our pharmaceutical process in the same way. We characterize our unit operations, we integrate it into a process train, and in this case we've got feeding, PAT, compression, and then we'll integrate that into our factory. A little thanks there to Gaia and GCon for some of the images used. Okay, so let's look at that commercial process, and now we need to try and understand what are the similarities and differences between a semiconductor process and a pharmaceutical process. So we don't have a process, we have a tool, and we have a sequence of tools. This is discrete manufacturing. We have the chambers within the tools, and we're controlling the wafer quality throughout each discrete task. We perform a number of processing steps, 500 steps at least. So 500 manufacturing steps, and then we perform electrical testing at the end. Now let's look at our pharmaceutical process. So we have discrete, continuous or semi-continuous, and we have batches. The product can change both in terms of physical, chemical, biological characteristics. The product within the semiconductor industry is extremely high quality and very, very well controlled. We have intermediates. We're not able to provide the same precision of control because of raw material variability, uncertainty in our models. Final product quality is measured in near real time, but as additional CQAs are required afterwards, dissolution tests, etc. So we're going to jump between the two industries over the next few slides. We're going to look at the semiconductor plasma etching process as a case study, and then we're going to jump to some other activities, some other case studies with Takeda and also with the MMIC. Let's start off with our semiconductor process. So we're going to focus on the plasma etching process, one of the steps, a very important step. It's an extremely complex process, very difficult to measure. For in situ measurements are both invasive and difficult because of the size. We're looking at nano, down to nanoscale here. And it's essentially often run in open loop and the recipe derived from a DOE. We have sophisticated models, black box models, mechanistic models based on the physical properties, the bulk plasma properties, etc. And then we can use model predictive control. So we're using advanced process control, multi-input, multi-output, and sometimes non-linear. So we're focusing on this central control, this control loop. We don't have PAT, we have metrology, which is essentially the same approach in the semiconductor space. That can be virtual metrology, which is essentially a soft sensor or a mechanistic model, and we can have actual physical metrology as well. End-of-line testing is used, and we're measuring optical and electrical measurements. We may use a mechanistic model and possibly a Kalman filter as part of this control system. So keep that in mind, and then we're going to jump to an example in the pharmaceutical industry from Takeda, some recent results presented as part of our collaboration in Boston with the team there. And we're looking at essentially a continuous process for API manufacture. Multi-stage process, a Grignard's, coupling process step, quench, and then we go to an LLE, liquid extraction step. Bunch of chemistry goes on, some hexagons change shape. I'm an electrical engineer, by the way, you can tell. And we have the process steps that are continue through. So the customer wanted to telescope this process, make it highly autonomous, introduce APC, PAT, mechanistic models, utilize all those in an autonomous control strategy. And they wanted to use this to upskill their colleagues and have an academic and vendor partnership between ourselves and MIT. Many steps were went through in terms of an evolution looking at the PAT, and this is really the output here. So we have online FTIR, we have offline GC, titration, HPLC, with automated sampling. So a very sophisticated analytical suite. Process modeling. So we've seen this over the last few days in terms of the workflows. We perform in silico experiments to understand the design space, characterize the sensitivities, develop the soft sensors to predict our quality attributes. So the mass of magnesium, the concentration, the flow rates, and the CSDRs. And then we want to put that into an advanced process control system using a model-based approach. This is very much a quick summary of this approach, and you can see the type of performance that was achieved. This really brings together all the toys in one place. We have PAT, chemometrics, mechanistic models predicting our quality attributes, and then advanced process control controlling the process. When this works well, the data looks extremely boring. Everything's a flat line. Now, because of the speed that we delivered this project, there isn't a before case. You know, essentially, at every stage, we're bringing in the models. So very, very tight performance, very tight control of our quality attributes, active disturbance rejection, and you can see in the middle of the trend, there was a pump which blocked, and the APC was able to recover the process and drive it back to set points as needed. And at the end of the trends there, you can see we tried a few set point changes to show the robustness of the system. So going back to our etching process, let's have a look at our process here for the API line. Many, many parallels. We can see the PLS models, the mechanistic models, the Brooker, the PAT or metrology in the semiconductor example, and then the APC in the middle. So there's actually another layer to this. We talked about the inner layer of the plasma control system. There's actually another layer, an optimization layer, and that's what we call run-to-run or iterative learning. And this is essentially taking the output of each batch and then making a small adjustment to keep the process on track. In general, the semiconductor processes will work well, but they will drift over time due to deposition and other issues. So we need a run-to-run controller. And that's using a solver. We have an observer. In some cases, it can simply be just a filter, a UMA filter, which is looking at the previous data and the new data we have in place, and then making a small adjustment based on that ratio. So keeping in mind run-to-run, I now want to look at the second case study in the pharma industry, which is with the CPI. And this is looking at tablet press optimization. So in this work, we essentially pulled together a workflow to take 3 inputs, compression forces, and 3 outputs, weight, thickness, and hardness, to optimize our process. In some ways, this is really kind of digitizing the operator's workflow. So executing an algorithm, running the press, collecting the data, modeling, and then generating a new set of results. This worked extremely well. We can see here, so with 6 explorations, we're then able to optimize the process to any achievable parameter in terms of weight, thickness, and hardness. Now, it looks reasonably good. 6 steps, and then we can optimize with the 7th. But actually, this is a little bit of a cracking a walnut with a sledgehammer. the machine learning algorithm knows nothing about the process beforehand. And so a good operator could probably beat this algorithm relatively easily. So can we use run-to-run? With a mechanistic model and then some run-to-run optimization, I suspect we could even get to a better result more quickly. So that really brings us to conclude. What can we learn from here? So very different processes, but significant overlap in terms of techniques. But we actually drill down into the same questions. Which of these techniques is useful? Which methods will solve our problems? Is it frugal? Is it robust? How do we maintain it? So I think by adopting your mechanistic models, so if you control with PAT, we can really move from a position of semi-intelligence to at least augmented intelligence, and in the future, maybe even artificial intelligence if we get that far. So that's it. Really like to wrap up. Acknowledgements here. I'd like to thank the Takeda team, the MIC team over in Boston, the MMIC team here in Scotland, and also my colleagues from Applied Materials, David and Aparajith, and the excellent work that Jason did on the MMIC project, and everybody concerned. If you'd like to hear some more semi-intelligent ramblings, please come to our stand and we'll be happy to continue the conversation.
Thank you, John. I feel much comfortable now. I'm semi-intelligent as well. We have time for one question.
Question. Oh, I'm sure he makes. Right, I have a quick question. When you talk about the pump blocking, I would have thought of this, and I'm trying to say this is, I don't understand why you didn't have in-process control. So if you think about 30 years ago in the packaging sector, we would look at vibrations in a machine and know if something was going to go. So I would have thought surely there'd be some kind of feedback that says his pump is not quite performing, so you could have done a kind of preemptive strike without it breaking down. Or, or blocking your line, if I remember Happy Down down that bit. So I don't know, is that just not normal for your sector to do that, or is it just, it was unexpected that this pump kind of blocked?
So we started perceptive engineering to address that core problem of combining multivariate process monitoring, fault detection with control. You're absolutely right. You combine a process monitor to detect the faults earlier, alert the operators, take some action to correct. In this case, with the project, the focus was purely on control.
Okay.
So we didn't have that part of the technology. But yes, I completely
So it's a norm for the sector. You could do that and then have feedback
actually,
loops to keep it clean. Yeah.
Exactly right. And actually, you would combine the monitoring to monitor both the process and the controller's performance.
Okay. Thank you.
Thank you.
Thank you, John. Please reach out to John if you have more questions. Thank you very much.
Thank you.
Fantastic.